Hi, my name is Annaliese McDermond, NH6Z, and I am a senior DevOps engineer with the FlexRadio Systems software engineering team. And I'm here today to chat with you folks about the FlexRadio TCP/IP API and how you can use it to write your own software. I usually like to start out these things by telling you a little bit about myself. I've worked for FlexRadio for about 2 years now, and I'm the DevOps engineer, which means that I spend a lot of time worrying about how to build the software, how to deploy the software, operating systems that run the software, and things like that. So I worry about the Linux underpinnings of the software. I do contribute quite a bit of C code to the product, but I also spend a lot of time doing ancillary things as well. I started writing code when I was in kindergarten on BASIC on my Apple II, and quickly graduated to learning C in 6th grade and writing code after that. For my professional career, much of it, I got into doing systems and network administration and spent a long time doing network engineering for ISPs, running Cisco and Juniper routers and things like that. I got my first license when I was in high school at my high school amateur radio club and was licensed as KB7AKH in 1987 and got my extra in around 2000 when I was living in Hawaii. I've made some contributions to the ham radio community in some of my software that I've written. I wrote Buster, which is a client for D-Star reflectors on macOS. I also wrote Heterodyne, which is a client for the Open HPSDR radio series that runs on the Mac as well. I served as the vice president and a board member of Tapper for a while and supported amateur radio in that way. My deep, dark secret that I rarely tell anybody, for people that looked at my name on the opening slide, is that I am a member of the Oregon State Bar Association, and I've practiced law in the state before, although I'm not currently permitted to appear in court. So I usually like to start one of these talks with a good lawyer joke, just to kind of break the ice a little bit. So what do you call 1,000 lawyers at the bottom of the ocean? Most people call it a good start. So with that, we'll go and go into the presentation. The presentation is in 2 different parts. The first part, we'll be talking about the general concepts of the API, and we'll be doing that by me chatting over a bunch of slides. At the end, we'll actually be going into a demonstration of how the API works with a quick session and showing you folks how the radio changes as you issue it API commands to try and give a little bit of flavor to how it works and show you guys what the functioning of a real radio is. So let's chat about what the concepts of the radio. One of the important concepts of our radio is that really, out of all the radios out there, Flex radios are Ethernet native radios. We designed the radios with the Ethernet at the center of the radio and not some ancillary add-on where you can just do cat commands or simple little things that are ancillary to the radio's functioning. A Flex radio really cannot function well without its Ethernet port. And that includes the ones that are have front panels on them, because the internals of a M series radio, there's actually an internal Ethernet switch that connects the front panel to the rest of the radio. So even your radios with front panels rely on Ethernet to even function. That's why when we first came out with the Flex 6000 series, sometimes we called them radio servers, because some of the use cases that people actually use them for is to put rack rails on them, put them in a rack, and their radio will stay far away from where they actually operate it. The remote ham radio guys do this sort of thing where they have remote places where people operate it. All communications with the radio are over the network. There aren't any special interfaces or anything. Yes, you can put a cat cable on the back of it, but that's definitely a bag on the side for us, unlike other radios where the Ethernet is the bag on the side. So serial ports are definitely not native for us. And some examples of the nativeness of the Ethernet. The PTT and the frequency on Power Genius and Tuner Genius, which are our amplifier and high power tuner products, are actually transmitted over the Ethernet to the radio. Your amplifier will find your radio and you tell it which one it is, and the amplifier logs in through this API we're about to talk about and tells the radio what frequency and the PTT is happening on there. The virtual ports that appear when you use Smart SDR for Windows, so DAX and CAT, are all implemented over Ethernet as well. We connect to the radio over these TCP and UDP streams that we're going to talk about, and then we provide virtual serial ports and virtual sound cards to the Windows machine itself. And one thing I really want to emphasize to you folks is we eat our own dog food with this. There is no separate API that we use for Smart SDR for Windows and Maestros and things like that that we do not give you, the software developer. The same API that we give folks is the same one that we use to implement everything. So you should be able to implement anything that you can do in Smart SDR for Windows yourself using our API protocol. We don't hide it. There's no encrypted passages on the network, no SSL on it, which, you know, some people may complain that that's insecure, but it is what it is. And there's no authentication with the port where you have to have a special handshake to tell it that you're Smart SDR. The same API that we use for Smart SDR is the same API that you can use to control your radio as well. So let's talk a little bit about the network API. There's a standard API that we publish to use the radio over the API port, and we publish that out to the public. The canonical reference for that is on our wiki at wiki.flexradio.com. It is sometimes incomplete and outdated in ways, and we are trying to fix that and maybe even automate it, but it's the best source of information that you have over the API right now. And later on in the presentation, we'll mention some other places where you might be able to get some enlightenment. There are actually implementations in various languages as well that you can use to get yourself a leg up on how to implement the protocol. The biggest one of these is FlexLib, which is a C# implementation of talking to our radios. FlexLib is actually what we use in Smart SDR to do the low-level radio communication. And we publish that to the public and developers so that they can use that as well to get a head start if you're running Windows and you're doing C# sort of stuff. I can't, and in the question and answer at the end of this, I can't answer very many questions about FlexLib because I work mostly on the radio side of things, which is Linux-based. So I am not a strong or really at all a C# programmer. So I can get you access to resources where you can ask questions about FlexLib, but I am probably not the resource to chat about FlexLib. There's also a nascent Python implementation that some folks that are developing GNU radio blocks for the FlexRadio 6000 series are using and have actually published on PyPy now. It's called Flex Client, and you can get that. I believe they state it's in heavy beta, but if you would like to contribute to the project, I'm sure that there are folks that are more than happy to have your contributions as well. There's also an interesting Arduino implementation in C, C++ that a ham radio operator has used to create an Arduino Maestro to remotely control his radio with a tiny control panel, which is pretty great and really a sign of innovation and the flexibility of the API. You might be able to repurpose some of those API components if you were doing another C, C++ project to use the Flex API. And the last one that I'll go over is a personal plug. I have published a Python project that is kind of a stupid Raspberry Pi trick project, and it is for an on-air sign that my wife gave me for Christmas 2 years ago that came out of the KUT studios apparently and was used on Austin City Limits. And I was deciding how to best use that great piece of equipment. So I put a Raspberry Pi inside of it, and I can turn the light on and off with the GPIO. The Raspberry Pi will log into a Flex 6000 series radio and sit there and listen for the PTT to go on and off, and when it does, it will light the sign using the GPIO. All that code is open and available on my GitHub page. And one of the interesting things for folks to look at is that there is a separate class in there that uses Twisted Python to implement the low-level FlexRadio protocol. So that's something that one could probably steal, and I give folks permission to do that, although I don't think I remembered to license it under the GPL. You are more than welcome to steal that library and use it in your own code as a base. Let's talk about some examples of programs and things that use the FlexRadio API. One of the really hot ones right now is Node-RED. And Node-RED is kind of a graphical programming environment where you can drop and drag blocks and connect them together in order to create complex workflows or to create different dashboards for yourself that you can customize to be able to operate and automate your radio. And there are some folks that have come out with some FlexRadio blocks that you can drop in and do certain things. And there are some folks publishing Node-RED panels based on that you can use as well. It's really pretty exciting. Mike, who works for us, has been very involved in that community and doing some cool things. So that's something definitely to check out if you're not that strong a programmer, but you'd still like to do some customization on your radio. There's also SliceMaster 6000, which is a program that can automate a bunch of the stuff on your radio. So for example, every time you would like to run FT8, you can create a SliceMaster profile that will open your FT8 client, WSJTX, as well as put the radio into all the modes that it needs to be in order to make WSJTX work, to turn on the DAX connection and move frequencies and change the mode, etc., and so forth. So it's a really handy tool to do that. That uses our API. This one's kind of a cheater, but SmartSDR for Mac and iOS, our partner that writes that protocol, or those programs, actually uses the same protocol that anybody else can use to make that work in order to create clients for other platforms. So you could use this API if you were so inclined to create a Linux client if one wanted to. There's also an interesting one that we actually end up using in the software engineering group called FlexMeter that will show you meters coming from the radio itself in more of a raw format and enable you to enumerate them so you can get temperatures out of there and things like that on different componentry because we do provide those meters out the API port. So it's rather interesting to look at them and to be able to debug them. We actually use it as an example client to debug some of the meters to make sure the radio is sending them correctly. So some information sources that you can use to get some more information about the API. As I mentioned before, the canonical source is the FlexRadio Wiki, and you should look on there as kind of your first resource to be able to grab information on the protocol. But another place you can go to ask for help is the FlexRadio community. We actually have a separate category of folks that are just exchanging information on the API and how to use it and their struggles with their programming they're going through. So it's definitely worth asking a question on the FlexRadio community. And some of our service and some FlexRadio personnel actually monitor that and look at it. And sometimes if there's something that software engineering can become involved with to help you out, they will refer it to us. There's also an email address, devhelp@flexradio.com, where you can email to try and get help from us. This is kind of a best effort email, and we will respond to you when we do have a chance. Software engineering tends to be busy. We're a small team and have a lot of work, but there are other folks in the service and marketing folks that monitor that address and help us out as well. So if you do email that, we will try and get you a response as quickly as we possibly can. The other great resource that I'd like to mention is Wireshark, because as I had mentioned, there is no secret handshake. We do not encrypt the connections going to the radio, so you can actually sniff the exchanges between a client and the radio on the fly using Wireshark. So if you are curious about how Smart SDR does something, when you click on the screen, you can actually go and turn Wireshark on, click on the screen, capture the packets that go between the radio and the client, and see what commands that Smart SDR gave the radio in order to make that happen. If an intrepid soul wanted to, one could probably actually make a module for Wireshark that you could plug in and decode all of those exchanges within Wireshark. Nobody's done it yet, but that doesn't mean that it can't be done. The documentation is out there to make it happen. And another thing that I'd like to mention in passing is the Waveform API, which is a close sister to the API components that we're going to be talking about implementing a client. And it's a way to create new modes for the radio. When it's a plug-in module that you can tell the radio about, it connects in and registers itself, and it actually comes up as a separate mode in your mode selection on Smart SDR or any other client that you have out there. And it can run either on the radio, and we have a way for you to upload those modules to the radio if they're in the proper format, or it can run on an external computing device. The reason why that's important is that the radio doesn't necessarily have all the processing power that it needs to do some of the heavier duty waveforms that you might put on there, especially if they're not optimized yet. So if you have problems with that, you can run it externally on some sort of other device. It's also great for development because you can do all the development and run it on your PC. Make sure it runs correctly before you go and try and upload it to the radio, where you have significantly fewer debugging facilities up there. You're not really going to be able to run a debugger on the radio with how we have it currently set up for external people to access. It is based on the same API components as a client connection, the same TCP connection that we're going to talk about, the same UDP streams that we're going to talk about. And what we'll be doing at Flex is that we actually have a helper library that's going to be coming out soon that handles a lot of the lower level stuff for you, so you don't have to worry about it in the Waveform API. And you can more concentrate on what your algorithm is and what your SDR components have to be. There's also a GNU radio block that's associated with that builds on the Waveform API library that we'll be releasing so that you can create GNU radio graphs and implement new modes that way. And an example of a waveform project is this link, which integrates FreeDV as another mode into the radio. This isn't ready for prime time yet and still has bugs to work out, but it gives you an example of how the whole system works and how you can create a waveform. So that's just in passing to let folks know that the client API isn't the only API out there. We do have a way where you can actually add modes to a Flex radio. So let's talk about the different network streams that you are going to use in the API. There's a TCP stream on port 4992 on the radio that's for command and control. That's really the mother stream of the radio, and you're really required to have that stream before anything else. So the way of using the radio is to connect to 4992, and everything happens after that and flows from that command and control port. But other than that, we also have UDP streams that transfer some of the more real-time data into the radio. So, streams like slice audio, so the audio that's going to come from your receivers. Stuff like the pan adapter and the waterfall, we will give you the values that you need to draw those on the screen over UDP packets. The DAX and DAX IQ streams are also on there, so you're talking about the raw data that you can get and you can route to sound cards and things like that. Those are over UDP packets. And amazingly enough, meters, we meter in a quick enough fashion and at a large enough rate that we send the meters over UDP as well. Some of their meters refresh pretty quickly, so it makes it impracticable to send over the TCP stream. So we just send them to you in UDP packets. So more about that TCP stream that's kind of the mother stream. All the command and control comes over this stream to the radio. There's really no commands that get sent over the UDP packets. Those are mainly just for transferring data back and forth to the radio in a real-time manner. And that includes mode changes, tuning, AF gain for the outputs that are actually on the radio. In this way, it's not unlike SIP, Session Initiation Protocol, for those that are familiar with that, where SIP handles all of the call setup and the dialing and things like that, and then RTP handles the transfer of the actual voice data between the PBX and the telephone. So it's the same way. R4992 is very much like SIP, and the UDP packets are very much like RTP. They serve kind of the same purposes for those that are familiar with those protocols. There are three basic messages that come back and forth between the radio in the TCP API. The first one is the command, and the command is sent from the client to the radio, and that's instructing the radio to do something. All of these commands are signified with the first character of the line you're going to send the radio. The protocol is line-based, and terminated with a new line, a Unix new line, as the end of the command. So it's very line-oriented. The C is the first letter of the line, and that gives you the command. What's going to happen when you send a command is the radio is going to send an R back. So there will be an R in the first position of the radio sending back to you, and that's for response. So the radio is going to send the response back to you. Then the third major one is a status message, and that's an S, and that's going to come from the radio to the client, and that's the radio telling the client that something is happening, or the status of some sort of component, like the current frequency of the slice maybe, or whether PTT just turned on or something like that. That's going to be S messages, and we'll see some of those as we go into the demo portion of this talk. The status messages are on a publish-subscribe model. There's a command that you send called sub that allows you to subscribe to different kinds of status messages, so you just don't get flooded with things. So there's a lot of different stuff that happens on the radio that we can send you in status message, and you don't necessarily want all of it for whatever your use case is. There are certain things that you get by default when you connect, but the rest of them you actually have to subscribe to. So the UDP streams are all based on VIDA49, which is an industry standard format for software-defined radios. The link there is not the official documentation on the VIDA49 format, because that tends to be pay for, where you have to buy it from the standards body, unfortunately. But there's a lot of information on the VIDA49 format that's on the internet. The link there just happens to be the one that I always end up using, because it's got the packet formats pretty nicely outlined on it. Wireshark also has a VIDA49 module in it, so it can decode some of this stuff for you in VIDA49. The payload of the VIDA49 packet will vary by the type of packet that you're getting, because there are a few different things that we can send over the VIDA49 packets. And there are markers inside of the header and fields that you can use to determine how that payload might look. The VIDA49 is never sent unsolicited, so just by connecting to 4992 doesn't mean that you're going to get streams. You actually have to ask for them from the radio to initiate the streams in there. We won't really see how a lot of that works, because I don't have anything to conveniently catch UDP, but you actually have to subscribe to those streams in different ways and get them started to send to you. Again, not unlike SIP and RTP, where you're not going to automatically get an audio stream just because you connect to the SIP port, because some clients may not even want audio. For example, the on-air sign that I created, that client doesn't ever want you to want the radio to send it audio. It's unnecessary for its job, so we don't automatically send it. So you pick actually what port you receive all those UDP packets on as the client, and you tell the radio what you've got, and it'll use that port to send your UDP packets to. And that concludes kind of our lecture portion of just giving a brief overview of how the API looks. So that should give you some basis to understand what the demo portion next is going to show you. So let's see if we can jump into that. In this screen in the background, I have a copy of SmartSDR connected to my Flex 6700 here at the shack in Lebanon, Oregon. And on the antenna 1 input, I have a dummy load so that we don't disturb anybody with our API experiments. And on RXA, I have a receive-only loop on top of the house that is connected up and live. So we are going to show you how all of this works. The first thing that we're going to do, if you look in the window in the lower left, which is on my Mac with a terminal session, we're going to go and see if we can get logged into the radio. You can use, on the Mac, we're going to use NC in order to connect, which is their way of creating an arbitrary TCP connection. The NC should be available for like Windows subsystem for Linux. NC is available for Linux natively as well. Or you should be able to use PuTTY to do this if you don't have anything else on your Windows client. So I'm going to use NC, and I'm going to go to Flex 6700, which is my radio here, the name of my radio here at home, on 4992, as we discussed before. And you can see that we've now connected to the radio. And the radio, because we connected, we're subscribed to certain status messages, which you can see, for example, here is a status message that is coming back and letting us know statistics about the radio and the status of what we've got going. You can see things like how many slices and pan adapter the radio has available on it. It's the 6700, so it has quite a few. You can also see the radio's nickname that shows up when you browse to that on the radio chooser, and my call sign that's programmed into that radio. You also see interesting things about the filter sharpness on CW and voice that it updates you with when you first connect. So those are examples of status messages as you get them back and how those get used. So those are great status messages, but we're going to be doing a lot with slices in this example. So I'm going to subscribe to all the slice data. And how we're going to do that is we're going to issue a C command. The thing that comes after the C command is a sequence number. We're going to use sequence number 0. And usually what we do is we go from 0 to infinity, and each command gets a unique sequence number to it. The main purpose of the sequence number is because we're going to get a response back from the radio, and those responses are not necessarily in order that the commands are issued. They can come back in a different order than you issued the commands. So the response will have a sequence number that matches the commands that created the response, and we'll see how that works in just a second here. So it's going to be C0, then we use the pipe symbol, sub for subscribe, slice, all. We'll subscribe to all the status updates for slices. We're going to hit return. You can see we got some more status messages here that we're getting because we subscribed to the slice. And that's mainly because the radio tries to send you a fresh copy of the status messages every time you subscribe to one so that you have a baseline of what's going on at the moment. But the more important thing is here we see that the radio responded to that command and gave us a response back with the R message. The R, after the R is the 0, which matches the C0 that we sent it before, so that's sequence number 0. After the bar is a hex code for an error code that comes back from the radio. 0 means a successful command. Anything else is an error. And anything else will be a hexadecimal code that represents the error in the radio. And you can look some of those hexadecimal codes up on the wiki. After the second bar is going to be sometimes you will get a text message back that further explains the error. It's not required of the spec, but sometimes we're nice when we code that stuff out and we actually send you an error message that means something. So there's our first successful command. What we're kind of going to do here is we're going to try and get the radio set up to do FT8 on 20 meters, not using the mouse at all, just using the API commands to get things set up for you. So let's see. The first thing that we've got going on is that the radio is not receiving very much. It's pretty dead, and it's around 9:20 here in the evening in Oregon. So there should be a lot of that stuff happening on 40 meters at this point in time. And the reason why that's not happening is I'm on antenna 1, which is hooked to a dummy load, which isn't a great antenna. So let's switch that receive antenna to the RXA antenna that's hooked to the loop on top of the roof. We're going to do C1 bar slice set 0, and the 0 is for slice number 0 that is open on your screen. RXANT, which is the receive antenna, and then RX_A. And the RX_A antenna is the input that goes to the loop on the roof. We're going to hit return, and you'll see immediately that the pan adapter in the back starts receiving a lot of signals, and we start seeing all the chaos that's happening. We also see the radio responds to us by the R1, and that it's telling us that the slice has changed in a status message. Well, it's nice that we're receiving signals, but we're receiving signals on the wrong band. So maybe we ought to tune this receiver to where it's supposed to be. And so let's tune it, which is C2 for the second command that we're going to issue. Slice, tune, 0 for we're going to target slice 0, 14.074 megahertz. And this frequency is always in megahertz when you're using this command. So that should be the FT8 frequency on 20 meters. So we're going to hit return. And you notice the pan adapter changes. And we get the radio is tuned to 14.074. So we're on now 20 meters. But the problem, that if we look at it, is that it's in the entirely wrong mode. It's in CW. And we're not going to be able to use the CW mode in order to receive anything on FT8. So let's change that to digital upper. We'll do that by doing C3, slice, set, 0, mode equals digu for digital upper. When we hit return, you ought to notice that the radio then changes. We see a little bit wider filter there, and it looks like it's on digital upper now, which is great. We're one step closer to getting our radio set up for FT8 for tonight. But I want to go a little bit extra, and the filter there is pretty narrow for me. I'd rather open it up a little bit so I can get all the different signals in there. So let's open it up to be a 4,000 hertz wide filter. So we're going to do C4 for the fourth command sequence, filt for filter, 0 for slice 0, 0 for the low cut frequency, and then 4,000 for the high cut frequency. When we hit return, it comes back, and you see on your screen in the back that Smart SDR shows that our filter is now wider. So the next thing we got to do is we got to set it up, and because we're cool and we're FlexRadio people, the FT8 goes into WSJTX over DAX, but we ought to set up the DAX audio so that it goes to the correct place. So let's do C5, DAX, audio. If I can spell audio. Set 1, and that's for DAX channel number 1. Slice equals 0 to tell it that DAX channel number 1 goes to our slice 0, and TX equals 1 means that the DAX TX stream also will go to this. So when we hit return, we noticed a couple status messages where it's telling us that the DAX configuration has changed, and the radio responds to that things are okay. So this should get us pretty much set up to receive FT8, but we're amateur radio operators, not shortwave listeners, so we should really see if we can get some transmitting going. But my dummy load is pretty weeny on the back of that thing, and I don't want to be really operating it at 100 watts coming out of the flex. So let's tune that down so that I can give my dummy load a break. We're going to do C6, transmit, set, RF power equals 1. Which should set RF power to 1 watt. When I hit return, you can see that the power slider in Power SDR came all the way down to 1, and now we're not going to blow up my dummy load on the back of the thing. But I'm going to want to tune this thing beforehand just to check and see if it works. So let's make sure our tune power is at 1 watt too, so that we don't tax that dummy load anymore. So let's do C7, transmit, set, tune power equals 1. And again, we see the tune power slider go down, and now we don't have to worry about blowing up my dummy load when we tune it. The last thing we really have to do before we can test transmitting is we have to set the transmit slice, the slice that's going to control the transmitter. So that's going to be C8, slice, set, 0, and the 0 is for slice 0, TX equals 1, meaning that transmit is on for that slice. And again, you see the transmitter interlock shows some changes in there, and the command is successful. So let's go ahead and tune up and make sure that the radio is working correctly before we go into transmission. So let's do C9, transmit, tune, on. And you should see the radio go into tune mode. You see that tune and the mocks come up, and we're transmitting a signal now, which is great. And if you were here in Oregon, you would hear the relays click in the 6700 and things come back on. So it looks like things work. Let's turn the tune off. So we'll do C10, transmit, tune, off. And now the transmitter is off again. So we're really ready to transmit now. Let's see if we can go and actually put a signal out and see if it works, which is C11, XMIT 1. Now the transmitter is keyed. We see that we got an R11. And we see that on Smart SDR, the MOX is sitting there and sitting on, showing you that the transmitter is keyed. And we see the interlocks showing that the state is transmitting. So I think we're done with transmission and having our fun for today. So that's C12 XMIT 0 to turn the transmitter off. So that's kind of how the protocol works, and you can control various things on the radio using just text. So again, the GUI client uses all these text messages to actually change how the radio behaves. Hopefully that's been a great demonstration for you, and hopefully you guys have learned something. I've really enjoyed giving this chat to you guys, and hopefully we'll have some great questions in the question and answer period. Thank you so much for attending. Again, I'm Annaliese McDermond, NH6Z, and we will talk to you in the question and answer session.